Okay, so if you recall the example that we had in with regards to the simple pendulum, where we had theta double dot to be equal to minus g by l sine theta minus k by m theta dot, we chose a Lyapunov function as g by l 1 minus cos theta plus half theta dot squared, with theta being between minus pi to pi and theta dot in the reals. Let's say we have this. So what we got is this turns out to be minus k by m theta dot squared, which is less than equal to 0 in the set that have been given to us, right? Negative semi definite. Okay, now, but from our experience, we know that the system under consideration is such that origin is asymptotically stable. But the choice of Lyapunov function here can only take us till the fact that origin is stable. So this is where LaSalle's invariance principle, okay, helps us. So what does LaSalle's invariance principle tell is, see, if coming back to the example, we could just prove origin is stable. We just need to show that trajectories will have a tendency to asymptotically go towards the origin. So asymptotic conversion to the origin is something that we have to establish. Once we establish this, then with stability coming from the Lyapunov function and with the fact that we have asymptotic conversion to the origin, this combined, we can have asymptotic stability established for the origin. Okay. Now Lassalle's invariance principle is a principle wherein it tries to establish that in the domain where the system is evolving, you will be able to find a certain invariant set, certain largest invariant set inside the domain, to which every trajectory will approach asymptotically. So if you start outside the set, the trajectories will approach the set asymptotically. Okay, that is what it is. So let's see what the statement formally says, and then we will slowly dissect it. So let omega be a subset of D, and let this omega be a compact set. To put it simply, it is the set should be closed and should be bounded. Okay, let omega be a compact set that is positively invariant, which means if you start inside the set with the system dynamics that you have, you'll always stay inside the set. And what is the system dynamics that we are considering? For this case, we are considering the system of the form x dot equal to f of x, and f is a map from D to Rn. Okay, f is locally it sits on D. So suppose this is positively invariant with respect to the system dynamics x dot equal to f of x. Let v be a function that maps from D to R. So v is a real valued function. Let it, and it is also continuously differentiable. Okay, let v be a continuously differentiable real valued function such that v dot of x is less than equal to 0 in omega. So notice here, it is not saying what v has to be. V can be signed indefinite, v can be positive definite, v can be negative definite. What it says is v just has to be a continuously differentiable function such that the derivative of v evaluated along the system is going to be less than equal to 0 inside the set omega. Okay, it will always be inside the it will always be negative, or it will always be non-positive rather inside the set omega. Suppose this is the case. Now inside this, let E be a set of points, set of not just points, set of all points in omega where v dot of x is 0. So collect all those points in omega where v dot is 0, because v dot x is going to be less than equal to 0. So collect all those points. That set is E. Now v dot is 0 at a point does not mean that v dot is going to remain 0. Okay. Now inside this set E, you find the largest invariant set. Meaning if v dot is 0, then v dot will remain 0. Find all those points for which if once v dot is 0, v dot will remain 0. Okay, that is what it means. Let M be the largest invariant set in E. If we can find this largest invariant set in E with all these conditions, we'll have that every trajectory or every solution that starts in omega will approach the largest invariant set M as t approaches infinity. Okay, so what essentially is it is saying is omega is a subset of D. It is positively invariant with respect to the system under consideration. V is a map from D to R such that V dot x is negative semi-definite for all x in omega. E is a set such that V dot x is 0. M is the set of all points where V dot x is identically 0. So this triple equal to essentially means that V dot x is equal to 0 for all t greater than equal to 0 is what it means. Okay, if this is the case, so let's say this is the domain D, this is the set omega, this is E, and this is M. So then what it says is no matter where you start, you'll always approach this largest invariant set asymptotically wherever you start in omega. Because omega is positively invariant, trajectories cannot escape omega. And note that if you are already inside M, you have been inside M for the past time and you will be inside M for the future time as well, because M is invariant is an invariant set. Invariant with respect to what? With respect to again the system dynamics that we have. So if you can find such a invariant set inside the set omega, then what it would ensure is every trajectory that starts in omega will always approach m asymptotically. Every trajectory that starts in omega outside m, okay, will always approach m as t approaches infinity. So this is LaSalle's invariance principle, and you notice here it is talking about asymptotic convergence. Now, if you recall the proof of Lyapunov theorem, we had constructed a positively invariant set omega. So that positively invariant set can set here. If that is the positively invariant set, and if we have a v which has v dot to be less than equal to 0 in the set omega, and if we can find the largest invariant set, then the trajectories will converge towards this largest invariant set. Okay, and suppose the largest invariant set that we have in hand is nothing but only the origin, which is the equilibrium point of the autonomous system, then it means that all trajectories starting in omega will actually converge asymptotically towards the origin. So this establishes asymptotic convergence. Now for stability, or we already are saying v dot has to be less than equal to 0. If in addition to that we say that no, v cannot be just any function without any sign definiteness, we'll say v is positive definite. So with choice of v being positive definite and v dot being less than equal to 0 in the set omega, establishes that origin is going to be equilibrium point. Origin is going to be a stable equilibrium point. Further, inside this set omega, if you can find the largest invariant set M, where v dot remains identically 0, and suppose this only consists of the origin as the point, then it means all trajectories will converge asymptotically towards the origin, which basically means origin would be asymptotically stable. So the stability comes from the fact that v is positive definite continuously differentiable function and v dot is less than equal to 0. The asymptotic convergent part comes from the fact that v dot is less than equal to 0 and there is a largest invariant set m where v dot is identically 0, and it happens that origin is the only point in that largest invariant set, which ensures asymptotic convergence. Together, it ensures that origin would be asymptotically stable. So this is a corollary that has been derived from the LaSalle's invariance principle. Note that LaSalle's invariance principle just talks about asymptotic convergence. It does not talk about stability. Okay, we can talk of stability only when we add the property of positive definiteness. Okay, so let's see what the corollary states. So let x equal to 0 be an equilibrium point for the system x dot equal to f of x, where f maps from D to R and f is locally Lipschitz. Let V be a map from D to R. Let this be a continuously differentiable positive definite function on the domain D. Okay. Let the origin be in D. Rather, I should write it like this: on a domain D containing the origin such that v dot of x is less than equal to 0 in the domain D that we are considering. Let S be a set of all those points where v dot is equal to 0, and suppose that no solution can stay identically in S other than the solution x3 being identically equal to 0, which means the largest invariant set inside the set S only has the only point which is origin. Okay, origin is the only point which is in the largest invariant set. If this is the case, then the origin is asymptotically stable. Okay, so v dot v has to be continuously differentiable positive definite function, and v dot is less than equal to 0. Origin is in the domain under consideration. S is the set of points where v dot x is going to be 0, and suppose that no solution other than x being identically equal to 0 is will be able to stay inside the set, meaning xt so origin is the only point in the largest invariant set, then in that case origin is asymptotically stable. Now you can also conclude global asymptotic stability. How? D will be Rn. In addition to whatever you have, V is, so this is, I'll write a plus here. This means in addition to whatever you have, V is radially unbounded, D is Rn. Origin is a unique equilibrium point. With this, we'll have origin is globally asymptotically stable. Okay, now to understand this, let's come back to the example of the pendulum where theta dot was minus g by L sine theta minus k by m theta dot, and the v that we had chosen was g by L 1 minus cos theta plus half theta dot square, with theta being minus pi to pi, theta dot being in R. So the d was minus pi to pi times R. Okay, and what we got was v dot to be minus k by m theta dot square, and we had this to be less than equal to 0. So in a positively invariant set, we know that we have a function v which along the system dynamics will be less than equal to 0. Okay, now S is a collection of all those points where v dot is equal to 0. So this essentially means x is a, so what is x? I'll define x. X is nothing but theta dot transpose. So x is such that theta dot is 0. This is coming from the expression of v dot. Now theta dot may be 0 at one instant of time. For example, when the pendulum is swinging and is at the extreme end of its swing, okay, that is when theta dot is 0. Okay, so it can have theta dot to be 0 at extreme points, but still the pendulum can keep on moving, which means that even though theta dot is 0, you can come out of the set S. So the solution that you have got, which is the angle theta and theta dot equal to 0, will not stay in S. Though that is a part of S, as time progresses, you will see that the system moves out from S. Okay. So the largest invariant set M will be such that X belongs to D where theta dot is identically 0. Okay. So that is theta dot is equal to 0 for all t greater than equal to 0. For all t, it should not be for all t greater than equal to 0. It should be for all t. I think in this case also, when I say identically 0, it is for all t. Now, so this is M. Now, how do you find what are the points in M? Okay, so if theta dot is identically 0, then it means that theta double dot will also be 0. Note that when theta dot was just equal to 0, does not mean that theta double dot is going to be 0. It is 0 just at one point of time. But here theta dot is 0 for all time. So it's basically constant at 0. So theta double dot will be 0. Theta double dot is going to be identically 0. Now we have a dynamics that we have for theta double dot. So what I can do is I can substitute for minus g by L sine theta minus k by m theta dot to be identically 0. This essentially indicates, so theta dot is already identically 0. So this gives me that theta is identically 0. Okay, so the only point that we have in M is the 0, 0 point. And this is a equilibrium point of the system. So we have a positive definite continuously differentiable function v for the dynamics that we have in hand. We have v dot to be less than equal to 0. The largest invariant set is a set which contains only the origin, which is the equilibrium point of the system. So what is our conclusion? Our conclusion is origin is asymptotically stable. Notice Lyapunov function could only take us till the fact that origin is stable. With this Lyapunov function, we had v dot to be negative semi-definite, so we could only conclude origin is stable. With the aid of LaSalle's invariance principle, which brings in asymptotic convergence, we were able to now add the asymptotic property to the origin. So origin is asymptotically stable. Okay, so I suggest that you try further more examples or try questions from the assignment and see where you can apply LaSalle's invariance principle and proceed towards the conclusion of asymptotic stability. In case Lyapunov functions, in case the derivative of v does not turn out to be negative definite. So we'll stop here. Thank you.